Welcome back. Switching to, switch to shared content. Okay. Full screen. All right, let's go. Perfect. All right, hope you guys are doing fine. I know that this is kind of a crunch time for everyone, and the class participation is also kind of gradually reducing as people get used to more videos. Um, but uh, but as I said last time, interesting. Nothing is being shared. Why? Technical difficulties. No technical difficulties. As I said last time, what we said until last lecture was part of your quiz 2. Starting today, we're going to talk about a new module, main memory, and whatever I say today and for the rest of this class will be part of your final quiz, which is in the exams week. Okay? Quick reminders, projects, CA2, and homework. CA2, people ask about like the criteria for getting full grades and all. Basically, it's more of an educational project. Personally, that's the type of project I would like to have in my classes, where you kind of like learn a new topic and then it's based on you how much time you want to spend on it. You can spend a lot of time, you can spend as little time that you want. It's really based on your interest rather than me kind of like forcing you to spend time. If you feel like doing more, do it. You're gonna get more points. If you don't, you don't. Okay. Let's talk about main memory. So last time we talked about memory hierarchy, and we told you that we want to have both fast and large memory, right? And we talked about caches as kind of the main tool to achieve this. And we talked about improving the performance of the cache, the structure of the cache. And we said that eventually what happens is that the performance of a cache boils down to 3 important metrics: the hit time, the miss rate, and the miss penalty, right? And we gave you a lot of different ways of optimizing each of these metrics, and you saw that some of these techniques kind of impact both or multiple of these metrics. We talked about a little bit of replacement policies and structure of the cache and so on and so forth. And as I said, we talked about how to improve each metric. Hopefully you've understand all that. It's a very dense, the previous lecture was very dense lecture, so you may want to watch it a few times to understand all the concepts. And of course, you don't need to memorize any of that. You just need to understand them. So now today we want to kind of go one step down. So if you remember, our cache hierarchy was like this. So most of our class, we focused on this part, and we told you that registry essentially is kind of deeply integrated into the CPU, so it's part of the data path. Then last time we talked about this part. Now let's actually talk about this part and this part. So this is additional part of the memory hierarchy. We're still within the same realm of memory hierarchy, but we want to talk about what we call main memory and then secondary memory, which we usually call disk. Okay. So the technology that we use for main memory is DRAM. DRAM is much, much slower than SRAM. As a result, main memory is significantly slower than your caches. But the good thing about DRAM is that it's very dense, which means that you can store a lot and lots of data. So main memory is significantly larger. So if you remember, we last lecture, we talked about kind of different sizes, and we said that main memory DRAM technology, we are talking about gigabytes, order of tens of gigabytes, right? So like, even your cell phones these days has like 8 or 16 gigabytes of RAM. And when you say RAM, that means the DRAM, okay? Yeah, another thing that happens with DRAM is uh, is that DRAM and disk together is usually called main memory, okay? But keep in mind that their technologies are different and they're kind of like primary memory and secondary memory. Um, when we say memory or main memory, we usually refer them both. And we will show you later that why we kind of assume that these are all part of the same system. Think about it as kind of different level of cache kind of thing, but it's not really that. It's a little bit more complicated. Uh, Once we assume that the main memory and the disk are together, then every access to the main memory is going to be always a hit, right? Otherwise, you're like, basically it covers all the possible addresses that you can have in your system. You're not going to address something that it never existed, right? So we don't have the notion of misses in main memory. This always hit. The problem, though, is that it takes much more time for the data to arrive. The second thing is that we need to kind of handle the data movement between disk and main memory, and that's what we're going to talk about in this lecture. Uh, but yeah, that's kind of like the notion of the technology. Okay? So let's actually talk about how do we store things in the program memory, in the memory, and what are the challenges that we are facing. The first thing that we need to understand is that we're kind of like taking a step back and thinking about this as more of like operating system level, program level. Um, so if I have a program and I want to store different programs, the very first thing that I need to have is the principle of isolation. Okay. So let's say, for example, if I have 3 different programs, the main thing that I need to provide in my main memory is isolation. Why do I need isolation? Because if program 2 can, for example, access any part of the main memory, then we are basically saying that by running one program, you can impacting other programs in your system. This obviously has many concerns, comes with many concerns, including the correctness issue as well as security issues. So imagine that, for example, you open a browser and your browser can mess things up in the rest of your program, including all your files, all your documents, and so on and so forth. So the first thing that you want to have when you're storing these different programs inside your main memory, which is kind of the main job of the main memory, is that you want to partition this nicely so that each program has its own kind of space, okay? Um, and then how do we what do we assign to each program in addition to have this isolation? We typically, within each program, we also have nice and isolated regions. We usually have code region, data region, heap region, stack region, and so on and so forth, okay? If you really want to share memory with multiple programs, you can have that as well. So you can have shared spaces that multiple programs can read and write to. Um, and then, of course, you will have your operating system, and your operating system should also reside in your main memory. So we typically reserve some part of the memory for operating system and its libraries. And then we can allow, for example, programs to read and access some part of this reserved space or operating system related space. Uh, you can also allow things to be read-only or read and write, uh, um, which means that you can also read things without really writing things or changing things. For example, for the operating system, that's probably what you want to have for each program. Okay? Once we have this, then the question really becomes that how do we manage the memory? How do we manage the content? How do we move things around? What will happen if you want to add a new program and remove a program? What if a program wants to grow or shrink? And these kind of things. And then, of course, the second question is, how do we actually send this data back to the cache and from the cache to the CPU and so on and so forth? So the story that we want to cover in this lecture is about kind of this memory management, okay? Memory management is typically controlled by a combination of hardware and software. Most of the things are actually controlled by the operating system, but there are many things that there are hardware support for it. We're going to talk about things such as address translation and page table, and you will see that hardware has an important role on all of that. Uh, and And as I said, you can think about memory management as a range of different things. So, for example, if you have a very, very simple, let's say, embedded system, then your memory management is basically simple. Essentially, you have just one program, and that program accesses everything. There is no isolation, there is no different regions, there's nothing like that. There's just one flat memory. And that was kind of like what we discussed in this class so far, right? So we said that, okay, these are the addresses. You just put the address, you get the data, and that's it. In real system, though, as I said, your memory is kind of fragmented into multiple parts. Even within those parts, there are regions. And then there are various different regions that may have read or write accesses to each other, and so on and so forth. And then you can kind of dynamically need to change this because a program starts and a program ends. So you need to kind of like also allocate or disallocate memory as you're kind of running things. Okay. Um, so let's just start talking about how do we share the memory for multiple programs. And this is kind of the basis of what we call virtual addressing, which is kind of the key part of the main memory, and we're going to talk about that. Of course, the first idea that comes to mind is that if I have multiple programs, the first thing that I can do is that statically partition my memory and assign different, partitions to each program, right? So let's say, for example, say that I can support 2 programs. I'm going to divide the memory in half, maybe a little bit less than half, so that I have some space for some reserve addresses. And then what I'm going to do is that I'm going to say that, OK, this range of addresses is for this program, this range of addresses for the other program. That's all I need to do, OK? And when I do this, in order to enforce that isolation mechanism that we talked about, essentially what we need to do is kind of having something like this, that we need to have what we call protection bounds, that if the CPU tries to access the memory, the region, we need to check and make sure that this is within the bounds of the program. If the address is larger than that bound, then we need to do something, like doing bounding violation and so on and so forth. For example, segmentation faults is an example of that. That's one thing. The second thing that we need to provide is our program should be kind of location independent, which means that the absolute address in a program should not matter because everything should be kind of relative. If tomorrow I decided to move this a little bit up or down, my program shouldn't break, okay? So the way that we're going to do this is basically by having this kind of concept of base plus offset that we have seen in this class, that we never have absolute addresses. We always have like a base address, and everything else is relative to that base. As a result, addresses relative to that base stays constant regardless of where you're going to put your program. If I switch these two programs, the addresses relative, for example, to this base is always the same, regardless of where this base is. All you need to do is just changing this base. Every address relative distance to that base is going to stay the same. Okay? This is what we usually call location independence property. And the first one that I told you is the protection property. Okay? So the solution, as I said, for these two problems is that for location independence, we're going to use a base pointer. And for the protection, we're going to use the bounding checks. Together, they're going to look something like this. So your address is coming from the CPU, OK? What you're going to do is that you take this address, and usually you add it to the base registers. Okay? So the address that is coming from the CPU is typically the relative address to the base of the program. Okay? So address 1 is not really address 1. It's actually address 1 plus whatever the base address is. Okay? This address, we typically call it physical address because this is the actual address that is addressing the memory. On the CPU side, you might have like address 1 or address 2 or address 3. They may not access actually memory location 1, memory location 2. They might access, let's say, 1001 and 1002. The difference between this kind of CPU address, which we later going to say that this is what we call virtual address, versus the actual physical address is that there is some form of a translation going on. In this case, it's very simple translation. It's essentially you add everything to a base. But in modern systems, this translation is more complicated, as we're going to talk about later in this lecture. Okay? Not only we do that, we also need to check the bounds. And the bound check is very simple. You just need to see if that address is within some bounds that you accept. And again, here you check the relative address. You don't need to check the absolute addresses. You just check the relative address of the request that is coming from the CPU. For example, you say that, okay, my program should have only access to whatever base address is plus and minus 1,000, okay? So if I see an address anywhere between minus 1,000 to plus 1,000, I'm going to allow it. Anything beyond that has to be blocked. So this way we can make sure that the program is isolated. Of course, here we are assuming that the programs are continuous, right? So there is like a continuous region of a program that we're going to use. Later on, you're going to see that that assumption is not also always true. Any questions so far? Great. All right, so this is, as I said, this is what we call address translation. So essentially, a physical address, we typically show as PA, is equal to some form of a base register that we have, some base pointer that we have, plus what we call the logical address, or sometimes called virtual address. Logical address is the address that we use inside the CPU, right? So 1 and 2 and 3 and in our programs, right? So in our programs, for example, we have address 100, right? Like, all the things that we saw so far, these are all relative address to whatever that base is. If I change that base, all those addresses will change too. Yeah? The question is, can we use logical and virtual address interchangeably? Sort of, yes. I mean, logical, so this is still not virtual. Yeah, maybe not, actually. Yeah. But logical, you can call it effective address. That's also what's been used in many resources. Okay. Okay, so now that we kind of like understood that, okay, the simple solution is static partitioning, and I can have a base pointer, and I have a bound check, and this will work fine. And honestly, in many systems, that's actually all you need. There's a few other things that you need to also consider. For example, what if we want to share something between these programs? Let's say, for example, I want to have some libraries. Think about your standard libraries, such as like, a standard C libraries like printf and scanf and those things. One thing you can do is that you can copy it for every single program, right? So you can add it to every program. But of course, that's a very inefficient way of using your memory. What you can do is that you can have it somewhere as kind of standard libraries, and everybody can have access to those libraries. Of course, in order to make sure that the system is secure and the isolation properties maintained, everybody only had read-only access, okay? So they can only read those files, but they cannot write to them. So they cannot modify printf and scanf. But you can obviously call them and use them by passing numbers and all those things, okay? Drivers is the same idea, interrupts and interrupt service handlers, all those things. So essentially, these are services provided typically by the operating system. They're all in like part of your libraries that can be shared, okay? And then the last thing, of course, is the OS itself. You can assume OS as a program as its own, right? So we typically treat it similarly to any other programs that we have in our system, right? So typically we have lower addresses of the memory just reserved and dedicated to the OS. And again, most cases, if program wants to, let's say, have a system call or access the operating system, we kind of call it mapping the addresses of the operating system into the program. So essentially, calling this function is still counts as within the bounds of this program. So they can actually easily call those functions within the operating system. But of course, they are not allowed to write anything to the operating system. If they do, then again, that causes lots of security issues. Okay. Um, so far so good, right? So it's straightforward and great. And as I said, many systems does this like this. Actually, many systems don't do even multi-program and multi-tenancy. Like simpler computers actually have a single one linear memory, just one program, and that's it. Modern systems, of course, cannot do this. So for example, if I want to add a new program, because that's typically what you do in your system, right? So you open a new window or you close a new window, you call a new terminal. You do constantly adding and removing processes in your system. With this static approach, unfortunately, adding and removing programs is not easy, right? So for example, in this particular case, if I want to add program 3, there is no space left for program 2. So either I need to kind of like remove things from program 1 and program 2, which is might actually cause lots of correctness issues for these programs, or I need to somehow like kick program one of the programs out and replace it with the other program and so on and so forth. So it's not a straightforward solution for dynamically adding and removing programs. This works nicely if during the actual program phase, I know exactly which program goes where. Otherwise, I cannot dynamically add or remove programs. Um, and then another thing that might happen is that not only just programs, but also you can assume that different or existing programs may want to change their sizes, right? Remember that many of our systems are actually having stack and heap. And stack and heap is actually not just a confined space, they can grow, okay? And if they grow, then essentially the static space that we assign to them may need to actually grow more. And you can say that, for example, okay, I'm not going to let a program to grow, but that will lead into performance issues and utilization issues because, for example, let's say program 2 only needs this much and program 1 could benefit from growing. If you don't let that happen and say that, okay, no, I'm going to like divide it this half, then probably you're going to waste the space that could have been used for program 1, right? So you also want to be allowing the systems to kind of dynamically grow or shrink as long as their correctness are not hurt. So based on these problems, static-based kind of programming is not the most desirable, especially for high-end and performance-sensitive systems. Of course, the option 2 would be switching from a static format to more a dynamic format, right? So what we're using in all of these modern systems is some form of a dynamic partitioning of the memory, okay? Dynamic partitioning of the memory, unfortunately, comes with a lot of challenges because now you need to kind of like, move things around and add and remove things and so on and so forth. In order to fix that issue, what we're going to do is we're going to divide the memory into much smaller blocks, and we call these blocks pages, okay? So these are fixed size blocks, typically 4 kilobytes, sometimes bigger in other operating systems, but typically 4 kilobytes. And this 4 kilobytes is a continuous space region in your memory, okay? Essentially what happens is that then you take your memory and you divide your program into these multiple pages, okay? So your entire memory actually would look something like this, that what used to be like one program and another program is now a sequence of many, many pages, small pages, okay? How many pages depends on how large your memory is, right? So for example, if you have an 8 gigabytes DRAM, then you're going to have 8 gigabytes divided by 4 kilobytes if this is your page size, and that would be the number of pages you're going to have in your system, okay? So going back to what I was just saying is that, so the first thing that we're going to do is that we're going to divide the main memory into smaller chunks called pages, okay? Once I have that, then what I'm going to do is essentially I'm going to think about each program as some combination of these pages, right? So for example, let's say I have 3 different programs, program A, program B, and program C. And for example, each program might have 4 pages at the beginning, okay? What happens then is that, as I said, each page is 4 kilobytes. And remember that you still want byte addressability, right? So which means that I want to access each page, but I want to also be able to access a byte within that page. That's why we usually have, if the page is 4 kilobytes, I need 12 bits to address individual bytes within this 4 kilobytes, okay? So that's what we usually call page offset. That means that within that 4 kilobyte page, if I want to just select one byte, I use that page offset to go and grab that byte, okay? Keep that in mind, and usually that 12 bits is the lower bits of the address. All right, so going back to what I was saying is that, okay, I have a bunch of different programs. Each one has multiple pages. I want to still be able to access the bytes within the pages, and I'm going to use what we call page offset. But then how do we scatter this into the main memory? We're going to scatter it page by page basis, okay? So we can have, like, essentially we can divide the memory also into the pages, and we assign this kind of like different pages of different programs into the system. You had a question? So the question is, why do we need 12 bits for accessing the page? No, we're not selecting the page. I'm saying that, let's say I want to access something within page 0, okay, or within page 1. Each page is 4 kilobytes, okay? So in order to be able to access individual bit, I want to just read 1 byte. How do I access 1 byte within a 4 kilobyte page? I need 12-bit address. I need log2 of 4 kilobyte, which is equal to 12. Mm-hmm. Yep. Yes. So we still haven't talked about the how do we select the page itself. Well, let's say I magically select the page and I want to bring the address, bring a byte from that page. Later going to talk about how do we actually select the page and how do we find the page. That's actually an additional problem that we're going to have. Cool? Yeah. Yeah, so page number is actual identifier of a page. But then within each page, you have addresses from 0, let's say, to 2 to the power of 12 minus 1 kind. Mhm. Yes. Yes, 4 kilobytes is typical in most systems. There is also a notion of what we call huge pages, which is usually 2 megabytes or sometimes different. But that's really depending on the type of operating system. So Windows is different than Linux and different than Mac OS and so on and so forth. But 4 kilobytes is almost standard. But there's nothing wrong if you choose that you want to have 8 kilobytes pages. That's also fine. All right, so let's see how our memory looks. As you can see, our memory can look something like this, that my pages can be scattered around my main memory. Operating system still can reserve some space. And by the way, the operating system itself can be page-based, right? Uh, but the very quick problem that you're going to see here is, first of all, what I'm doing here is that I'm no longer kind of having a continuous space. The reason for this is that I want to use my memory more efficiently, because now I can basically assign or allocate or deallocate space to each program at the page's granularity, right? Which means that if a program wants to grow, I'll add another page to it. If the program wants to shrink, I remove page from it. If I want to add a new program, I'm going to find this empty pages in my memory and assign it to that, and so on and so forth. So essentially, what used to be big chunks now are smaller chunks, and then they no longer needs to be all bunched together. Still, within each page, it needs to be continuous, but across pages, it doesn't need to be continuous. Based on that, I'm going to have a big problem, and that big problem is where I'm going to find each page's story, right? So now that for example, I want to read something off of this page number 1 and some byte from page number 1, now that now that I know that my pages are kind of scattered and could be anywhere in this main memory, I'm gonna have a lot of issues or kind of figuring out where my pages is. Okay. Uh, in order to fix this issue of pages could be anywhere into the memory, we're going to need a table to keep track of the mapping, okay? So essentially what we're going to do is that for each program, we're going to have a table, and this is what we call a page table, which what it does is basically storing the beginning of each page, okay? So for example, if my program has 4 pages, what I need to do is having a table of 4 entries, and within those entries, I'm going to have the pointer to the beginning of the page. That's all I need, right? Because I know that my page is, for example, 4 kilobytes. Every address that I want to find is essentially P0 or P1 plus the page offset that I have, okay? This way, I'm now free to store the pages wherever I want. All I need to do is just storing the addresses and saying that, okay, the first page, the first part, like first byte of first page is stored here. The rest you can find, okay? And I need to have this for every single program that I have in the system. So if I have 4 programs, I need 4 of these tables in my system, okay? As I said, this is what we call a page table, and then for usually a page table is combination of all these programs together. So you have, for example, let's say if you have 4 tables, they're all together. It's called page table. Okay. So now that I have page table, then I'm going to introduce a new concept, and that is what we call a virtual address. So virtual addressing is this trick that we're going to say that, okay, now that you tell me that for every address that I have here, I need to first go and see where the base is, and then I can basically find the relative address to that system. Now I can completely decouple the way that I address things in my CPU versus the address that are actually used in my main memory, okay? So basically, this is what I call virtual addressing, okay? The reason that I want to have virtual addressing is that every program, they don't need to know where their pages are stored. They don't need to be worried about the fact that consecutive pages are not in consecutive addresses and all. What they can do is that they can always assume that their addresses start at 0, 0, and it's always continuous, right? What we can do then is when we are translating virtual to physical, we actually go and find first which page this address belongs to, and which byte within that page, and where that page is at, stored, and all those things. So in the background, at the hardware level, what we're going to do is that we take this virtual address, and we actually kind of translate it into a real physical address and accessing the memory that way. But the good thing about this approach is that although it comes with this additional overhead of translation, is that every single program considers the memory for itself. It thinks that it has access to every single address in the memory. All the addresses start at 0, and every address is continuous, right? So it's essentially the program has this illusion of a large, a private, and a uniform memory. In reality, though, since we want to have this dynamic behavior and we want to add and remove things, we have all these tricks in the background. But if you consider like the way that you write a program, you never have this abstraction of pages when you're writing a program. And that's the beauty of this address translation, okay? So this is the process, okay? So we're going to have what we call virtual addresses, and you can also consider your virtual addresses as kind of different pages. Your virtual addresses then first goes to the page table and find the corresponding page for each address. Then it finds the pointer to that page and goes to the memory and grab that page from the memory. And then within that page, then you have the page offset to select the address that you want. And that is the address that eventually going to go back to your CPU or to your cache and whatever. Okay? this is the process of what we call address translation. So from your program, you will have virtual addresses. From your virtual address, you're going to translate it into physical address. And from physical address, you can actually access the real memory. You're going to get the data, and you're going to forward back the data all the way to your program. Okay? Um, and this is kind of like what it looks like, all right? So for each program, we think that we have access to the entire physical memory. Let's say you have 32-bit addresses. It's perfectly fine to address anything in that 200, 2 to the power of 32. And as I said, each program is typically divided into regions. So you have code region, you have data regions, you have heap region, you have stack region, and they can grow in opposite direction. And the same story in program B, and so on and so forth. Okay? In reality, though, what you have is that you have limited space in your physical memory, and that's what you buy, right? That's what you have in your system. For example, you will have 8 gigabytes of DRAM, and that's all you have. You cannot magically extend it to 16 gigabytes of DRAM or 32 gigabytes of DRAM, and so on and so forth. Oops. Do we record? We don't record. Yeah, we record. Sorry. So I have limited physical space. Of course, I can go and pay more and buy more memory, but at any given time, my physical space is limited. I cannot just magically grow my physical space. Even though I add more and more programs, my physical space stays the same. Okay? So what will happen is that although I technically have access to every address, I only access each page. I only physically allocate a page in my memory when I do have valid data. Okay? So if I actually look into these programs, although, for example, I have this space for my code, this space my heap, or this space my stack, the actual allocated pages in my physical memory is significantly less. That's why I can run multiple programs at the same time. Okay? But at some point, my memory might fill up, right? So for example, if you open like 10 Chrome tabs, at some point you will see that your computer no longer responding. The reason for that is that your memory is full. You're no longer receiving kind of any sort of data, meaningful response from your memory. And since all of your instructions are kind of waiting for that data to come, everything in your processor is also stalled. As a result, nothing progress, right? So you're kind of like this frozen state. But as I told you, usually we have the main memory backed up with your disk, okay? So your disk is where your entire information is stored. You have terabytes and terabytes of data. So at that point is when like things are going to be kind of like moved back and forth between the memory and disk. And since the time for accessing things in disk is very, very slow, that's why you see that your program is really, really slow. At some point, once you have the new data, then your programs start to be unfrozen and continuing. Sometimes it actually like stay in some form of a hang state and never kind of recover. But typically, that's what will happen in your system. But again, in most cases, the reason that this actually works is that you're not actually, although you have this illusion as a programmer that you have access to everything you want, the operating system and the hardware does not allocate all the pages at the beginning of the program. It's only based on the demand. So if you need more data, they will allocate more pages for you. Okay? All right, so as I said, this is typically the way that we're going to translate the virtual addresses to physical addresses. If you need more detail, that's how we actually do the address translation. Okay, the address translation is this this kind of step that we take the virtual address and we find the equivalent, the physical address equivalent of that. Okay, how do we do it? You have to see the first thing that you have to understand is that your virtual address size might be different than your physical address size. As I told you, typically my virtual address size is based on the ISA. So for example, my addresses are all 32-bit, or my addresses are all 64-bit. That's typically what we understand as the virtual address. That's the address that we're dealing with in the CPU side, right? So for example, like generally you can assume that this is 2 to the power of n. Okay. Your physical address size, though, is, as I said, is a physical parameter. It has nothing to do with the ISA. It has nothing to do with the microarchitecture. It has to do with what you actually physically bought for your system. Okay. As a result, the number of bits that you're going to have in your physical space is some other numbers. It might be ideally the same as your virtual address space, but in reality is much less than that. Okay. And your page size, as I said, is typically some specific number. Typically is 4 kilobytes. In other words, P is typically 12. Okay. But again, depending on the operating system, you can change this number as well. There's not like a specific rule that enforces that this has to be always 12. It could be other numbers, but typically it's 12. Okay. So based on this, we're going to have a virtual address like this. As I told you, since I need my address to be byte addressable, whatever my page size is, I'm going to have log2 of that as my page offset. This part basically selects the byte that I want to read from the memory. Okay? Since this is kind of like the offset to whatever base that we have, we typically don't need to translate this page offset. So the virtual page offset and the physical page offset are exactly the same thing, because both of them are offset to some base. The difference between virtual and physical is that that base is changing. Okay? So you don't need to change the offset as well. Okay? What really changes the virtual page number that now needs to be translated into the physical page number. Okay? So your virtual page number is essentially your consecutive addresses in your program. You can assume that, okay, your addresses start from 0, and then every 4,906 addresses becomes one page. Okay? So if your address is within the range of the first 4,906, this is page number 0. And then the next one would be page number 1, and so on and so forth. Okay? But then this page number now needs to be translated into a physical number. As you can see, essentially the translation is translating a number, an n minus 1 minus p bit number. I think there's another minus 1 here. To an m minus 1 minus p minus 1 number here. So essentially, I'm getting a larger number and translating it into a smaller number, right? That's why there might be multiple pages that technically be mapped into the same page. That's why operating system doesn't allow that to happen. That's why they don't assign multiple pages. They don't allocate pages unless you need them. Okay? So this is basically what happens with the address translation. All right? To give you like a more concrete example, let's say, for example, your virtual memory space is 4 gigabytes or 2 to the power 32. This is a 32-bit address ISA. Your physical size, let's say you're not very wealthy, so maybe you bought like a very small DRAM. It only has 256 megabytes or 2 to the power of 28 bytes. Your page size, as I said, typically is 4 kilobytes. That means that it has 2 to the 12 bytes. So if you start thinking about the number of bits that you're going to have, your virtual address space is going to be 32 bits. Your physical address space is going to be 28 bits. Your page offset is going to be 12 bits. If you count the number of pages, you're going to have 2 to the power of 20 different pages, because each page is the virtual space divided by page size. In other words, you're going to have 20 bits of virtual page number, or VPN. And then your physical space is 2 to the power of 28 divided by 2 to the power of 12, or 2 to the power of 16. In other words, PPN, or physical page number bits, are 16. So you need to translate 20 bits to 16 bits based on the page table. Okay? So your page table is going to look something like this. Essentially, think about this as a table with indices. This number, this VPN, is going to be the index to this table. And And then based on that, we're going to store the actual value, the ppn value here. So whatever content that we have here, that will be your ppn. So for example, in the example that I gave you, this is a 20-bit number, which means that I have 2 to the power of 20 different indexes in this table. Within each, I'm storing a 16-bit number. And this is the physical page number that I have. Okay? So I'm going to take that number. I'm going to put it as ppn. I'm going to take the page offset here as well. So I'm going to have a 16 number here, and I have a 12 number here. I'm going to concatenate these together. Then I'm going to have a 28-bit number. That is my physical address. That is the address that I actually literally take and access the memory and read the value and take it back. Okay? Question? Yes, the question is that wouldn't this make the page table huge? And that's true. And we're going to actually talk about, in reality, what really happens. To kind of quickly answer your question, not everything in this 2 to the power of 20 is actually valid pages. So you only store valid pages, which is significantly less than this. Mm-hmm. Yeah. So the question is, what will happen with collisions? So since you have mapping, at some point you might run out of the pages, okay? And that's why, as I said, when the processor not gonna, like your CPU gonna crash, so your program gonna crash. But again, this is not gonna happen in most cases. So in most cases, you have enough pages. You have enough physical memory. But if you open a very large program and you have many other large programs, then your system crash. Okay. So as I said, there is one entry per address. For now, let's assume that there is one entry per address. And this is how we're going to actually access this. Okay? I also told you that every program going to have its own page table. So how do we actually incorporate that into this translation? Typically, this table itself has a pointer, okay? And this pointer is per process. So if there is process 1, this table pointer, this base address of this pointer changes. And then when we go to the next process, we change the base address. So essentially, the VPN itself is the offset to a base address. That base address is the base register for every process. Okay? So for example, if I have 8 different processes, what I'm going to have is that I'm going to have 8 different registers. Each register store a pointer. And then whenever I have an address from one process, so for example, if I have address from process A, I'm going to take the base register A and then add the VPN of this to that. This will give me the PPN. Then I'm going to take the page offset from here and concatenate that page offset with the PPN. And that will give me the physical address. That will be the exact address for the exact bytes that I need to read. Okay? And then the next time, for example, if I want to address the next byte, what will happen that the next byte is probably the page offset is just page offset plus 1. So I'm still going to have the same PPN. My page offset would be plus 1. As a result, page address, the physical address plus 1 would be the next line in the memory that we're going to read. So you're still going to have some form of that locality that you want. The locality now is at the page granularity. So at best, you can have 4 kilobytes of locality. Okay? Because the next page is not guaranteed that the next page is going to be right after the next one. It might, it may not. Okay? So keep that in mind. So what do we store in each page table entry or PTE? As I told you, the main thing that we store in each page table is the PPN, the physical page number. And for example, if you have 16 bits, then like 2 to the power of 16 different addresses in physical memory, you need 16 bits to store here. In addition to that, each page table entry typically has also metadata. Okay? This metadata is various different flags that we store. And these flags are those flags that kind of tell you whether you have access to read this page or not, whether you can read to this page, whether you can read from this page, whether you can write to this page, uh, whether this page should be cached or not, and so on and so forth. There's actually quite a few of these flags that you store here. So this could be multiple bits. For example, there are pages that we call uncacheable, which means that there are things that we don't want to at any point cache it into my cache. There are various reasons for this, including performance reasons or security reasons. So if, for example, the flag here is equal to 1, I'm not going to cache this page. There is another flag called like read-write, which means that I have read-write accesses to this page. So in order to kind of enforce the bounds and the isolation property and read-write property of each page, all I need to do is that during the translation process, I also read these flags and check those flags. Okay? So this is actually quite beneficial and very, very handy and very efficient. Also, some pages, for example, are not executable. Okay? Some pages are instructions and some pages are executable, which means that I cannot like use this as an instruction if it's not executable. The reason for this is, again, also security reasons, because there are tons of these attacks that inject things into the memory and execute them. So you don't want that to happen. So if you've probably heard about buffer overflow, which I'm sure most of you have, one way of defending against buffer overflow is that making sure that your pages are not executable. If it's not executable, then it doesn't matter what you inject. You can never run those programs in your system. Okay? So generally, what I want to say is there are tons of these flags. What are those flags and why they're important and all that? You will probably see it in an operating system course, or you might already seen it in an operating system course. Okay? So now that we understand the kind of mechanics of address translation, let's also talk about how do we actually store and where do we store the page table. And the answer is that page table itself needs to be stored somewhere. And the only option that we have is storing the page table itself inside the memory. Okay? So what will happen is that essentially access to any memory is in fact two accesses. The first access is the access to the page table for address translation. The second access is actually the true access that you wanted to have. Okay? The reason for this is that we don't know where to store the page table. So the first thing we do is that going to the memory and actually grabbing that page table. Then we actually see what the content within that page table is. We're going to have a new address, and then we're going to go and grab the actual data. Yes? So the question is, why don't we have a separate page table? Because page table is large. Okay? So you need a secondary memory for that, right? So you need a memory for your page table. Usually you store it inside that memory, because then what's the point of having an extra hardware when you already have a memory? That's kind of the idea. So it's some form of a buffer, right? So what we're saying is that that buffer is actually within your memory. It's not like a separate memory, because it's large. The question is, wouldn't it be faster? It would be faster, but it comes with like large overheads that we cannot afford. But you're going to see, we're actually going to do lots of tricks to make this fast, so don't worry about that. All right, so essentially the actual memory, when we say a memory access, reality is that memory access is really two accesses. The first access is for getting the VPN plus base, okay? Once you get that VPN plus base and read the content of that, then you're going to have PPN plus page offset, and that's when you actually, the second access would be that, okay? So the first access is whatever VPN you have plus the base, which is coming from the process, and this will be the address that you're going to access in the memory to bring PPN. So this will give you PPN. You get that PPN, you add it with the page offset, and this will be the actual address that you're going to access to the memory. Okay? So let's also talk about how large a page table is, and that's already we discussed this. So let's say we have, again, 20 bits for VPN, 28 bits for physical address. Let's say I have roughly like 4-ish bits for the flags and other things. Uh, so what I'm going to have is roughly, I'm just making assumptions here. Actually, you don't, you have to reduce the offset as well. But let's say, for example, each page table entry, for the sake of argument, is 32 bits or 4 bytes. If you actually plug these numbers, you will see that you need about 4 megabytes for each application. Uh, right? So that's the amount of memory you need in order to, assuming that every single page in that application is assigned, you're going to need 4 megabytes of memory just for storing page table, not even the content of that application, just for the page tables, okay? And things are going to get much worse if you actually have a 64-bit address system, which is more modern systems are actually using 64. Here I'm assuming 32, okay? So you clearly see that page tables are huge. So we need to find a way to compress them. The second problem is, as I said, each axis is now two axes. And that means that immediately my performance is twice as low as I think it was. So I need to fix these two issues. I need to compress the page tables, and I also need to somehow make this axis for translation faster. We have a quick break, and then we're going to talk about these two things. Let's continue. All right, so how do we fix these two concerns? Let's talk about the storage problem first. How do we compress page tables? The solution to this is what we call hierarchical page table. So the idea is that let's store page table as a page table. That is, instead of having one page table, let's have page tables of page tables. And we're going to continue this to see what happens, okay? So the idea of hierarchical page table is this, that we're going to divide the address. Let's say I have two level of page tables. I'm going to divide my address, what used to be one VPN, to now two parts, part 1 and part 2, okay? Part 1, let's say, my VPN was 20 bits. So what I'm going to do is that now I'm going to say that, okay, the part 1 would be 10 bits, and part 2 going to be another 10 bits, okay? So what I'm going to do is that I'm going to first take part 1. So I'm going to take the base. Remember, for each process, we had the base address, right? So I'm going to take base address, but instead of adding it to the entire 20 bits, I'm going to add it to the part 1 bits, so the first 10 bits, okay? This is what we call level 1 page table, okay? From level 1 page table, what I'm going to get is another VPN or another address that points to the second level page table, okay? So essentially, if I have 10 of these, what I'm going to have is that essentially each one can point to one of these tables that I have here, okay? And then this will be basically the base pointer of second level page table, okay? From the second level page table, then I'm going to use P2 as the offset to select the new content. And this content is the actual PPN that I have. So in the past, remember, while I had the base plus VPN, now I have base plus P1 to get base of P2. Then I get that base and add it with P2. And now I'm going to have PPN, okay? And then PPN plus the offset, the page offset, going to give me the actual content. So this is the actual content. This is the actual physical address. These are still somewhat virtual addresses, okay? So what I'm doing is that I'm dividing what used to be one level of translation into two levels of translation. So you might wonder why this would be helpful, and that's a good question. By the way, this process is called walking. So we kind of walk through different page tables, okay? Uh, Modern systems have multiple of these levels. So I gave you two. There might be actually four of these walking. So you may end up doing multiple, four of these kind of level 1 and level 2 and level 3 and level 4, okay? So how does this help? So first of all, let's see how big this is. Uh, so what happens is that if you plug in the numbers, you will see that this plus this is actually going to be more than 4 megabytes because this one is same as your original page table, but now you are kind of adding multiple of this into your system. If you plug in the numbers, I'm going to let you do it. So essentially, for first, you need something like this because addresses are 32, and you have 1K of these. The reason that I have 1K of this is that I have 10 bits. And then the second one is that I have, again, each table is 1K times 4 bytes, but then I'll also have 1K of these because I have 2 to the power of 10, right? So I have many, many bits, right? So I have actually more than 4 megabytes of page table. So this is indeed actually not only helpful, but it's actually hurting you, both in terms of space and in terms of latency. So why do we do that? The reason that we do that is what I told you before, that not all the addresses are actually valid page tables. Especially the beauty of page table is that if for some reason the lower addresses are not assigned, this immediately remove entire second level page, okay? So for example, instead of storing every single full 4 megabytes, 1 kilobytes, page here, if this address is not assigned, like this higher address are not assigned, that immediately removes this. Or for example, if this is not assigned, that immediately removes this, okay? So what will happen is that this will allow us to look into the address, especially the higher bits of my address. If I only, for example, use addresses from 0 to 1,000 or something like that, in many programs that's the case, then many of these higher bits are going to be all zeros, which means that you actually never allocate the second level page table in many of these cases, okay? So you don't need to even store them inside your memory. That's how you're actually going to compress significantly your addresses, okay? For example, if more than 80% of this is not actually allocated, you're going to see that the significant portion of your second level page table, that's actually the kind of the bulk of the storage that you need, going to be gone, okay? So that's kind of like the basic idea that why these addresses are not like this. You also may wonder that why are we using higher bits and lower bits like this? And again, the reason that you're assuming that your addresses start from lower addresses, from zeros and all. And it's just kind of gradually go up, right? That's why you're assuming that you're not going to use the entire 32-bit address space. Doesn't mean that you're never going to do it. There are some programs that they might use it. But in most cases, you're not going to use higher bits. You're only going to use lower bits. Yep.
It seems kind of counterintuitive that a lot of virtual memory pages are just not available. The point of the need there is that, oh, we want to use all of it.
Yeah. Because then, remember I told you that I want my address space to grow. So there are most programs are very compact.
Yeah.
There are some rare cases that my programs are very large. So we're going to give this opportunity for every program to grow. But in reality, most programs are very compact.
I see. So basically,
Exactly. So the idea is that you essentially start with basically just one level 1 and one second level page table. As the program grows, you're going to add the second one and the third one. And think about discussion sessions when you're taking classes, right? It starts from like 4 discussion sessions. There's more demands, and we add another discussion sessions and so on, right? And that's kind of the idea. Okay. So this is what we call, as I said, hierarchical page tables. And as I said, this is commonly used in all modern systems. Uh, uh, since page tables needs to be stored themselves into the memory, we want to be able to compress them, and this way we're going to compress them. Of course, this, as I said, based on this assumption that the addresses are sparse, and most programs are very small. If the programs are large, your page table is going to be large as well, and at some point your page table is going to grow so much that you can no longer run more programs, right? But again, we're talking these days about uh, 64 gigabytes of RAM and 128 gigabytes of RAM and so on and so forth, which means that you have plenty of space for running these smaller programs. Smaller programs are order of megabytes and so. Okay? Okay, so let's go back to the second issue. So we kind of fixed the first issue. The second issue, by the way, what the trade-off here though is that I need more accesses, right? Because now what used to be one level of access now is even worse. It's now two level, for example. If I have two-level page table, every access to the memory now is three. The two for getting the PPN, and there's one for actually reading the memory. So that's a trade-off. There's not like it's not like free coming with this. So let's see if we can actually fix that issue as well. So each memory access is now multiple memory accesses. What can we do to fix this issue? Anyone has any solution for this? Any suggestion? How can we make the translation faster? Yeah. Exactly. So we're going to cache the translation, right? So remember what you do, what you use, and use that for the translation. Don't access the memory, access the cache. And we already know that the cache is much faster than memory, okay? The beauty of this is that, remember I told you that my addresses are within one page, and then like next byte is really within the same page, so I don't really need to do the translation. So that's where it's just going to be helpful. You translate once, and hopefully you can use it for the rest of 4 kilobytes data that you have, right? And even you can remember that, and then if you have, let's say, searching or moving between two pages, you can go back and forth between the two. You can always remember both translations. So each translation is essentially access to one level of cache. That's how fast this can be in paper, okay? This is what we call translation look-aside buffer, or TLB. The idea of the TLB is that when the address comes, instead of going through the process of address translation, I first look into my TLB, okay? If the translation is already there, I don't need to go and check my page table. I just took the value, the PPN value, add the page offset to it, and boom, I have my address, okay? If the address is not there, which is a TLB miss, then I need to go to my page table and do the page table walking and those extra addresses and bring that value from get the physical address and then take that physical address. So what is really happening is that if this is the virtual domain and this is the physical domain, what will happen is that once the address comes, we usually feed it into what we call a memory management unit, MMU. What MMU does is that it first sees that whether I've seen this virtual address, this VPN before, okay? Not the actual address, just the VPN part of it. So it can be any offset within that VPN, still fine. I check VPN and see if I have the corresponding PPN for it. If I do, then essentially I already have my PA. From the rest of this analysis, I can just take that PA and move forward. So all I'm adding to my access is one cycle of searching through that small table, okay? But if the address is not there, then I need to access the page table and I need to walk, so it will take a significant amount of time, okay? So the performance of the TLB becomes very, very, very important in your modern systems, because essentially every access, even in your access to your caches, because remember, caches also needs to have physical addresses. So even access to your cache, even though your cache is really, really fast, but since you have to actually access the page table first, every access to the cache is now equivalent to access to the memory. So it's horrible. So you really need to have a very good TLB, and that's very important in many systems and many designs. Okay? So what would be the hit time, as I said? So if the address is inside the TLB, for example, your access to level 1, the hit time of your cache would be the time takes for TLB lookup plus the time for L1 lookup. So your hit time slightly grows, uh, probably 1 cycle, because your TLB could be as fast as your L1. So this is still reduce the performance of your system, but not that much, because you also want to have virtual and physical addresses for other reasons. Remember, if I only had physical address, I didn't have this problem, but I really want to have virtual addresses for many convenient reasons that we just spoke. Okay? But the miss time is horrible, right? So the miss time is, it means that it has to go through the page table and then comes back and access the cache. So your average access time of your cache is now combination of a bunch of different things that we need to worry about. Okay. Um, so in order to kind of think about how this works is that, remember I showed you that there is a page table here. So what happens with TLB is that you take the VPN, you essentially store this VPN as the tag, okay? And think about this as a fully associative cache, that the tag is VPN, okay? You search through your fully associative cache and see if your tag matches with VPN, the result is VPN. So in cache language, your tag store, what you store in your tag store is VPN, what you store in data store is PPN, okay? If, and then once you get that number, then essentially that's your PPN. That's all you need to do. And then you just take the offset and then it's still concatenate. So still you don't need to translate offset. You don't need to store your offset in your TLB as well. All you need to store is your VPN, okay? So how many entries your TLB has? TLB typically has somewhere between 32 to 128. It's usually fully associative because we might have lots of conflicts, so you don't want to do that. You don't want very large TLB because it's fully associative, so it cannot have many rows. There are also larger TLBs, and if you have larger TLBs, then you need to have like a you need to have a set associative. So your TLB could be, for example, a 4-way or 8-way set associative as well. You might even have multiple level of TLB, similar to the thing that you have for the caches. You can have also level 1 TLB and level 2 TLB and all those tricks that you have for your cache. But the storage is significantly less. The replacement policy for TLB is typically either FIFO or random. Again, the reason is that TLB doesn't have the spatial and temporal locality, spatial especially locality, than your regular cache has. Because why? Because we are talking about huge addresses, right? Like the next two pages are 4 kilobytes apart in terms of actual addresses. That's why it's not very, in terms of spatial locality, you're not going to see the same patterns that you see in a cache. There's also a concept called TLB reach. This is TLB reach. It means that if your pages are 4 kilobytes, the size of your page times the number of entries that you have in TLB, that's the biggest continuous address that you can access without having a TLB miss, right? Why this is important? Because for many large programs, if you if you allocate consecutive addresses, then you can technically have all of these into your TLB and then run this without any hiccup. So every access basically becomes a TLB hit. But you are kind of like limited by how many entries you have in your TLB. So for example, you can have, let's say, 256 kilobytes of TLB reach, or something like that, okay? So again, this is mostly useful for large programs. Okay. Um, when we have a TLB miss, uh, this usually means that we need to stop the process of going to the cache. This usually leads to what we call an exception. Next week, we're going to actually talk a little bit about exceptions as well. This will cause an exception. Typically, the operating system takes over and going to go and translate this address for us using the page table, using the page walk. Then we're going to get the actual physical address, and then we can move on. So we kind of like service that exception and takes back the system. Okay. Alternatively, you can also do this in hardware. Like if you have a TLB miss, you can also implement everything in hardware. But since this is a slow process anyway, you rather want your software to handle this rather than your hardware. Okay. So this is kind of the story about pages and virtual addresses and page tables. There's one tiny optimization that I'm going to talk about it at the end of the lecture, and that is how we can actually make the access to L1 a little bit faster. But that's kind of it for virtual address and address translation. Any questions? All right, so let me also talk quickly about the disk. Remember I told you that my main memory is a combination of my DRAM and a kind of a secondary storage system called disk, okay? So how do we utilize disk? We utilize disk as kind of the background, okay? So we still have this paging system even in our disk, okay? So our data is stored in disk also in a page by page basis. But what we do is essentially we have this swapping mechanism or this demand paging mechanism where we store most of the pages, like we fill the DRAM with all the pages that we want, okay? And if there is a page that we want to access and doesn't exist in the DRAM, we take that page from the disk and swap it with one of the pages in the DRAM, okay? This is what we call page swapping, swap pages or page swapping, which you essentially fill your DRAM with pages that you have. When it's full, you kick one out and then swap it with another page, with the desired page from the disk. The idea is very similar to caches, right? So remember in cache, for example, in a fully associative cache, if all the entries are full and then there is a new entry coming, we have to select one of these entries and evict them from the cache. Same story happens here. Here we need to kick out or evict a page instead of like having an entry. And usually what we call is swapping the pages. So we take one page out and replace it with another page and put that page back into our disk. Okay? This is usually also called demand paging, which means that whenever we request a page, we bring it to the DRAM. So all of my pages are in my disk, obviously. Whenever we start the system, we start bringing pages uh, to the DRAM, okay? So as we request more and more pages, we bring more and more pages. And we allocate things in my page table. That's why my page table initially is empty, right? Only we bring things to the DRAM when we need a page, and that's when we actually allocate things in my page table, okay? If the page that we want is not in the DRAM, this process is called page fault, okay? So when we access a page and that page does not exist in the DRAM, we need to swap it. You're going to go to the disk and bring it to the DRAM and swap it with an existing page. This takes a lot of time because bringing value from this takes milliseconds of data. And that's what we call a page fault, which usually you don't want page faults to happen because page faults is really, really slow. Typically at the beginning, at the start of your program, you will gonna have lots of page faults. That's why it takes a lot of time for your programs to initialize. Once it's initialized, once you allocate all the pages that you're asking, then typically your program running very smoothly because now every access is either hit in the cache, hit in the TLB, or in some rare cases it's in the DRAM, and it's very, very rare cases it goes to the disk. Okay? So keep that in mind. Um, Again, so the way that we're gonna like actually know whether or not we store a page into our page table is having this valid bit. Okay, if we for any reason we decide to kick things out of our page table, we set the valid bit to equal to 0. So the first thing that we're going to check when we are doing the address translation is checking this valid bit. If this valid bit is equal to 1, then it means that this page exists in my DRAM. If this valid bit is equal to 0, it means that this page does not exist in my DRAM. This is a page fault. I need to go and grab it from my disk, okay? So essentially what we do is that we store a very large valid table, but the only thing that you store is 1 bit. So this is very small in terms of storage. But we have 1 entry per every single possible address, virtual address that we have, okay? So keep that in mind. And as I said, demand paging is when we are swapping. Then there will be lots of questions as in, okay, which one should I swap? What should I do on the update? All those questions that we asked and answered when we were talking about caches apply directly when we are talking about DRAM and disk, okay? So you can have replacement policy, you can have upgrade policy, and you can have all those things, okay? Um, and the kind of the thought process is very similar to what we had in caches. The only difference is, as I said before, the spatial and temporal locality that you're going to experience in DRAM and this is very, very different than L1 and L2 cache. Okay, so you're not going to expect to get many hits. You actually fix this problem by having big sizes, right? So you're storing each entry now is 4 kilobytes of data rather than just 1 byte of data or 4 bytes of data. Okay? And then another thing to remember is that from DRAM onwards, everything, including the replacement policy of bringing data and all, they're all handled by the operating system because this is incredibly slow. There is no need for having fast hardware to do this, okay? You have fast hardware for cache because replacement policy has to be very quick for L1 cache and L2 cache. For this, you don't need the speed. So everything is software developed and software implemented, okay? For example, you can have pseudo replacement policy or LRU policy. The overhead of LRU policy in software is significantly less than hardware. So you can actually have that because you can quickly write things, okay? All right, so that's kind of the updated picture that we're going to have. So we're going to have the CPU, the registers, the MMU. What MMU does is that it first checks the TLB. Most of the time, it's a TLB hit, which means that we have the address. From then, you're going to have the physical address. Then we're going to check the page table. If the address is stored inside the DRAM, it exists in the page table. So we're going to have the physical address. But also the address may not be in the page table if the valid bit is 0, which means that the address now exists in the disk. This is called page fault, and now we need to go to the disk and bring that value. So I no longer need the physical address. I need the disk address. I need to go and grab it from there. Okay? Any questions from this slide? Yeah. Yep. So the question is that the reason that it takes a long time to start a new program? Yes. Like opening like a large image takes a lot of time, right? So that's why. It stays in the DRAM and your caches mostly. Yeah. Yeah. Yes, the startup cost is compulsory misses. So if you have a knowledge of future that you're gonna open this file, then you can actually prefetch it into your system maybe. So this is actually what's called cold start. So for example, in high-end servers like AWS and all, that like since they need to kind of create a new process every time, since this creating new process takes a lot of time, they have this other mechanisms to actually quickly run a new process. This time that it takes to start is called cold start. So you want to make it hotter. Great. All right, so recap, page tables, we need them because we want to have dynamic addressing. We want to be able to add and remove programs. And we want each programs to grow independently and written independently. They assume to have all the addresses unique and private. That's when we need virtual addresses, and we need virtual address to physical addresses. Uh, in order to do this translation, we need what we call a page table. But page table has two problems. One is that it needs to be small, and the second problem was that it needs to be fast. In order to make it small, we use hierarchical page tables, which essentially we only assign a new page when we need them. In order to make it fast, we introduced the idea of TLBs, translation look-aside buffers, where essentially we remember the last few translations. This will eliminate the need for checking the page table, okay? So these two things makes things faster. The second problem is that not everything can fit into the DRAM. As a result, we will have disk, and we kind of need to opportunistically swap the pages between the disk and the DRAM. Similar issues that we have with cache and main memory exist between main memory and DRAM and disk. And of course, you need to be able to fix this using similar ideas that we had for cache, including replacement policies and update policies and all that. Question? Mm-hmm. Great question. So the question is about if you have instructions in the out of order, we have things such as load store queues. We put things in the load store queue, and we're assuming that we don't need to stall the process. We can find other independent instructions and run them into the CPUs. And then while we are waiting for like the data to come to go through hierarchy of the memory and maybe address translation and all that, then we can run other things, right? But then I also said that if, for example, we have a page fault, now the operating system needs to take over. And if the operating system needs to take over, it means that I need to kind of context switch between my current program and the operating system. And that's true. If I have only single core, then that would be what happens. So essentially, if there is an exception, then I need to stop that program. I need to run the operating system, which is another program, and then finish that and go back. So it would be very slow. In real systems, though, you have multiple cores, and that's the main motivation of having multiple cores. So your operating system really runs on one core, and your actual program runs in another core. Okay? So what happens is that these things happen in parallel. So your program can continue, your operating system can also continue. Yeah. Good question. So the question is, if there are multiple page tables from multiple programs, would operating system kind of group them together or not? Uh, sort of, it does. But again, usually we have multiple processes and cores. But yeah, you can consider that it's actually what's happening. We typically have what we call mishandlers. Okay, so think about each of these misses as a ticket, a request, okay? So you submit this request, and the hardware collects this request and either run them in parallel. Usually we can run multiple miss requests in parallel. This is called mishandler register, or MSHRs, okay? So you can actually handle multiple of this, because remember, you also have superscaler, you might have actually multiple of these, so you should be able to handle a bunch of these at the same time. All right, so last thing before I let you guys go is, remember I told you that if I have TLB, my hit time will be the time for TLB plus T of L1, right? Essentially, I'm adding the TLB in my critical path, right? So now the question is, can I make this better? Can I kind of somehow hide this number? Can I check these two guys in parallel? Okay? And that's what I want to do. So in order to do that, I need to somehow access my L1 using virtual addresses. Okay? Because remember, the address that I have from the CPU is virtual address. The reason that I need TLB is to translate this to physical address. That's where the TLB comes, okay? And all the accesses, including L1 cache, is based on physical address. If I want to somehow remove this and directly access my cache using virtual address, I need to have my cache somehow understanding virtual addresses, okay? But if my cache needs to understand virtual addresses, there's going to be problems. What is that problem? The problem is what we call aliasing problem. Why? Because remember I told you that different programs assume that their addresses start from 0 and goes down. They have no understanding whatsoever from the other existing programs in the system. So you might have an issue where you have two virtual addresses, both of them are virtual address 0. So how do you know which virtual address is the address that is stored in the cache? So you have two tags, right? And you need to somehow now know which process is which. So how do we do that? Uh, we're going to do this trick called virtually index physically tag cache, okay? So here's what we're going to do, okay? So if you look into the address, your virtual address, remember we had virtual page number VPN, and we had the page offset. Also remember that your page offset never translated, right? We always took the page offset and use it directly for both VPN and PPN, okay? So here's the idea. The idea that we're going to do is that we're going to use the page offset that doesn't require translation as my index to my cache, okay? So essentially what I will do is that I index my cache to basically select which row I want in my L1 cache. I bring the tag, I bring the data, then at the same time that I'm doing this, I also look up my TLB, and this is a fast tag lookup. I get my PPN, and then I will basically search and compare my PPN with the tag that I have in my cache. So what I'm doing is that I'm overlapping the process of selecting data from my cache, my L1 cache, uh, with the process of translating the tag, okay? What will happen then is that at this point, I have the tag from my cache, I have my PPN, and then now I can say that whether this is a cache hit or cache miss, okay? And then at the same time, I will have the TLB hits or miss as well. So ideally, if my TLB is a hit and my cache is a hit, what you will see is that essentially the time for this process is very similar to the time of accessing L1 or equal to the time of the accessing TLB. Both cases are basically the same, right? So it's as fast as what you used to have, because if the process of bringing the data from the cache if the process of look up the TLB is hidden in the time that we are bringing data from the cache, then I'm basically not going to see that translation address, okay? And this is why we call this virtually indexed, because the index is virtual, but the tag are physical. So virtually indexed, physically tagged cache. We call it VIPT, okay? What is the criteria? So by the way, what is the hit time? The hit time will be the maximum of this and the maximum of this, okay? And typically the max time is still, if I can make my TLB fast enough, I can make sure that this time is smaller than this time. That means that my lookup time of my L1 remains what it used to be. So I'm kind of hiding the time for lookup by the time of accessing L1, okay? What is the criteria for this? The criteria is that the number of indices that I have should be less than page offset. I cannot have a big cache that bits are more than the number of page offs. So for example, if I have 12 bits, at most I can have 2 to the power of 12 different indices. I cannot go beyond that, because beyond that means I need translation, okay? And if you actually look at that formula, you will see that your cache size should be associativity times the page size. That's actually how you can actually calculate this number. And I'm going to let you guys to think about how we reach to this number. But essentially what it says is that you cannot have more than 12 bits for index kind of thing, okay? And that means that your cache size, L1 cache size, cannot grow from some size more. So even if you have all the hardware in the world, either you have to increase your page size, or the only thing that you can do is adding more ways to your cache. So you can go like 16 or 32. You cannot add more sets to your cache. You cannot increase the index size of your cache, okay? All right. Any questions from here? Great. So last slide is, not all the systems going to have an MMU, a memory management unit. Not all the processors going to have virtual addresses. Just keep that in mind, that many simple processors, like usually in-order processors, have only physical address. So this whole process of TLB and physical page tables and all that is only for high-end processors. The reason for this is that this requires a lot of energy, requires a lot of logic, requires a lot of power, which smaller systems cannot afford, okay? But it comes with lots of convenience. For example, you can run multiple programs, right? Imagine that your laptop could only run one program. It would be basically useless, right? So you need this in high-end systems, but in low-end systems, it's only one program only, okay? All right. That's it for today. I'll see you guys on Tuesday. Next Thursday, yeah.